Hi, what if I asked you what's the easiest programming language to understand? You might say Python or JavaScript, maybe even Scratch. Does Scratch count? I don't know. But I'm here to tell you that none of those are the correct answer. The true easiest language to understand is Brainfuck. Now, what if I asked you what's the hardest language to use? Weirdly enough, the answer is still Brainfuck, and in my opinion, assembly would come in a close second. You see, Brainfuck is one of many esoteric or meme programming languages. Some of my favorite esoteric languages are Whitespace, Piet, there's Bfunge, and lol code. But Brainfuck is definitely the most popular of them all. I've been playing around with Brainfuck for a while now, and I've made something that I think is pretty cool. So, without further ado, I present 4 years of shower thoughts and probably over 200 hours of my life wasted on this completely useless and impractical project, compiling Pythonic to Brainfuck. Let's start with Brainfuck. As I said before, it's the easiest language to understand and the hardest language to use. The thing is, with only 8 commands, it really is beautifully simple, and yet that simplicity is what makes it so difficult to work with. Here's how it works. You've got an infinite array of 8-bit cells, a single pointer, and those 8 commands. The left and right arrows move the pointer. The plus and minus signs increment and decrement the active cell. The period outputs the ASCII key of the active cell. The comma reads the next character from input and stores it in the active cell. And then we're left with the square brackets. In a piece of brainfuck code, every open bracket must have a corresponding closed bracket. Code always just runs from left to right. When you reach an opening bracket, the execution jumps past to the corresponding closed bracket, but only if the active cell is 0. If the active cell is not 0, then the execution just continues on to the next command. When you reach a closing bracket, the execution jumps back to the open bracket and repeats. So these brackets are really the only way to create loops and control the flow of execution. And that's it. It really is simple to understand. Now let's talk about the hard part. Some common programs in Brainfuck are stupidly complex to achieve. Like, look at what you have to do to add 2 numbers in memory. Or even just hello world. You have to create the ASCII values for each character and then print them out one by one. Yet, somehow in all of this chaos, Brainfuck is Turing complete. Somehow this laughably primitive language is just as computationally capable as Python, Java, and C. So I figured surely it's possible to convert a modern language like Python into Brainfuck. And that's what I did. I made a custom Pythonic language that compiles down to Brainfuck. This example Fibonacci program compiles down to nearly 150,000 characters of Brainfuck code. If you were to run this on a standard Brainfuck interpreter, it would probably take a couple hours to complete. Maybe even longer than that. I haven't actually tried. To run this code, I had to use an optimizing Brainfuck to C compiler, and I'll add some more details about that in the description. At first glance, there's already a lot to unpack here in this example code, but there's one thing I really want to highlight. The language is able to handle 32-bit numbers, even though Brainfuck is in an 8-bit environment. Long story short, every number is stored in 4 Brainfuck cells, and that's just the tip of the iceberg. I put together a list of features that the language has. It's got dynamically typed variables, type checking, math expressions, if statements and loops, functions and classes, heap memory, along with malloc and realloc, inline assembly, and magic dunder methods. So how did I do it? I started by making a bunch of abstractions on top of Brainfuck. Easy snippets like moving the pointer forward or setting the value of a cell. Then more complex abstractions like conditionally running code, checking two cells for equality, or incrementing a number that's stored across multiple cells. After that, I decided on a structure for the infinite memory array. I treated the infinite memory array as an infinite array of 8 cell units, 8 byte units. Each unit had 4 cells for a full 32-bit number, and another 4 cells just for metadata. And as for all the units in memory, I denoted some as compute units, some as the program memory units, and then the rest of them as the stack. Next step was to create a custom assembly language along with the CPU in Brainfuck that could read and run the resulting encoded program memory. The most difficult part here was figuring out how to retrieve values from those memory units. Pretend you're trying to read the value of some label R0 stored at memory unit 3, or the fourth unit. This is a heavily simplified explanation, but here's what I did. I started by setting the marker cells for a compute unit and the first memory unit to 255. Now there's this Brainfuck code pattern that has been called a glider. It's a way to move the pointer until it finds a specific value. So I created a glider that moves 8 cells at a time, only checking marker cells until it finds that 255. I'll be honest, I got this idea from an awesome Brainfuck video called AI in Brainfuck. I'll link it in the description. Now we know the marker has to shift forward by 3 more units to get to R0. With the glider, we can repeatedly decrement, glide, shift the marker forward, and then glide back. Once this query cell decrements all the way to 0, we know that the marker is at the desired memory unit. Now it's just a matter of gliding some more to copy the memory unit's value back to the compute unit so we can use it. Setting the value of a memory unit is also just a similar process. With all the abstractions set up from before and having figured out memory access, creating the CPU implementation was mostly straightforward. Here's what the move instruction CPU code used to look like. And here's a picture of the old add instruction CPU code. Just to be clear, the Python code for the move and add instructions that I just showed is only being used to build up the code for the Brainfuck CPU. For performance reasons, I ended up with 32 instructions, but honestly, you could make something functional with just the 14 highlighted instructions. And finally, I made a hefty compiler that transforms the custom Pythonic language into the custom assembly. The custom assembly is then encoded into bytes and built up in the memory cells using Brainfuck code. I didn't talk much about the Pythonic to assembly compiler, but that's actually a whole other project on its own. So that's it. All the code is on GitHub. I'll link it in the description. I've also got a blog post on my website that goes into more details about this project. And there's even a demo page where you can write and submit your own Bufun code and get the compiled Brainfuck output. If you made it this far, thanks for watching. Let me know what you think and if this is something I should make more videos on.